In the previous video, we showed something called the mean value theorem for integrals, and it's stated as follows, that if f is a continuous function on a closed interval between a and b, there is a real number c that lives between a and b, such that f of c is equal to this particular value. It's the value of the integral of f of x over the interval between a and b divided by the width of the interval. Or if we multiply both sides of this equation by b minus a, we get this particular equivalent equation, which is a little bit easier to actually parse in terms of the geometry. But what we did not do in the previous video was look at any of the geometry. So we haven't really figured out what this particular conclusion of the mean value theorem for integrals actually says. And the other thing that is a big open question from the end of the previous video is, why are we calling it a mean value theorem? So those are the questions that I hope to answer in this particular video. So I want to start with that conclusion. So in other words, we are going to basically be assuming that f is continuous on the closed interval between a and b. So we do know that there exists a c inside the open interval between a and b with f of c equal to this particular strange number. It's the integral between a and b of f of x dx divided by the width of the interval between a and b, or equivalently f of c times b minus a. Let me clean up my notation just a little bit. Is equal to the definite integral between between a and b of f of x dx. And my real question is, what is the geometric meaning of this particular conclusion of the mean value theorem? And the way to get at that is to actually think very carefully about what the two sides of that equation means. So let me first of all draw a function. So let me get some nice axes here. There's a vertical axis and a horizontal axis, and I'm going to draw some kind of a function, and let's see. And so here is A, and here is B, and this, of course, is y is equal to f of x. And I kind of want to think in terms of looking at this area that I'm shading in white. And that area, of course, is known to be the integral between a and b of f of x dx. Now, what I want to do next is I want to think about what this particular side of my equation is. This particular side can be thought of as the area of a rectangle. And I kind of want to write that, and I'm going to put this in a different color. So let's put it in this color. F of c times b minus a is the area of a rectangle that has height equal to f of c and width equal to b minus a. In other words, the width of this particular rectangle is the same as the width of the integral area. And the height is just some particular point on the curve. And I'm going to draw it here because that looks to be about right to me. So this teal-colored rectangle, because the height of that point there is cf of c. So that teal-looking rectangle has area equal to f of c times b minus a. And the mean value theorem says there is a c such that, so there is a, let me clean this up. The mean value theorem says there is a c, oops, so there is a c such that the teal rectangle equals the white area under the curve. In other words, if I start looking at all of the possible rectangles that have height drawn by basically just dropping the height down from the function and making that into a rectangle, this one is obviously too big, and this one here would be obviously too little. But there is one that is just right. It's kind of like a Goldilocks theorem if you think about it. So the mean value theorem says there is an x somewhere between the two endpoints where, when we draw the rectangle, the area of the rectangle is just right. It is actually equal to the area underneath the curve. And if you think about it, what this means is that this particular height would work as an average value, where average basically means flatten this thing out and what value would you have if you just kind of said, try and make something that's flat instead of curved that has the same area. So basically what comes out of the mean value theorem is the following thing. We call the value given by the integral between a and b of f of x dx divided by b minus a, that is called the average value of f of x over the interval between a and b. And it's the average value of the function because if I make a rectangle that is that high, I get the same area as I get underneath the curve. And the reason the mean value theorem is called the mean value theorem is that the mean value theorem says there is an x where the height is the average value of the function. So let me state that very, very carefully. So we have this new definition that the average value of f of x over the closed interval between a and b is going to be given by the value of the integral between a and b of f of x dx simply divided by the interval's width, b minus a. And then in the context of this, the mean value theorem says, the mean value theorem for integrals, let's clean that up. The mean value theorem for integrals says there is a place between x is equal to a and x is equal to b such that the height of the function is equal to the average value of the function over the interval between a and b. And mean is a synonym for average in the world of mathematics. And that's why we call this the mean value theorem for integrals. It says that there is a place where the function's height is the average value for the integral.